Good morning everyone. In this lecture, I will explain about ideal Fermi systems. In the last 4 lectures, we discussed about the thermodynamics of ideal Bose systems, and we also discussed 2 examples for systems consisting of Bose particles. We already mentioned the condition for a system showing classical behavior or quantum behavior. And that condition depends on the value of n lambda cube. Here n is the number density of particles in the system, and lambda cube is h cube divided by 2 pi m kt raised to 3 by 2. So it depends on the mass as well as temperature. If n lambda cube is very much less than 1, then the system will show classical behavior. And this happens at high temperature or for a system consisting of heavy particles, and if the number density is very low. Okay, so these are the conditions favorable to show the classical behavior for a particular system. If this value n lambda cube is of the order of 1, and that will happen if this number density is very high or the temperature is very low and if the particles are very light. In that case, this n lambda cube will be of the order of unity and the system will show quantum behavior. And more interestingly, in this quantum behavior, the behavior depends on whether the system is made up of particles which obey Bose-Einstein statistics or Fermi Dirac statistics. If the system is made up of particles which obey Bose-Einstein statistics, that is particles having integral spin and with symmetric wave function, then the properties are entirely different, and we discussed these properties in the last 4 lectures. And if the system is consisting of particles which obey Fermi Dirac statistics, that is particles having half integral spin and with anti-symmetric wave function, the properties will be entirely different compared to the first system. Here we will not have the property like Bose-Einstein condensation and all, but we will have more interesting properties which are characteristic of fermions. So in the coming 4 lectures, we discussed about the properties of systems which consist of particles obeying Fermi Dirac statistics. Okay. The thermodynamics of ideal Fermi gas. For an ideal Fermi gas, we have these 2 equations. The first one is PV by KT. It is equal to log theta, where theta is the grand partition function. It is sigma epsilon log 1 plus z e raised to minus beta e, where beta is 1 by kt and z is fugacity. It is given by e raised to mu by kt. And total number of particle n is sum over the expectation or occupation values of number of particles, and it is sum over all energy values 1 divided by z raised to minus 1 e raised to beta e plus 1. Call these are equations 1 and 2 respectively. This is the general expression that we derived in lecture number 24. And for Bose particles, this A was minus 1. And for fermions, this A will be plus 1. That is why we obtained these 2 equations. And for system consisting of particles which obey Maxwell-Boltzmann statistics, this A will tend to 0. Okay, so these the equations we derived in lecture number 24. Okay, now the most important difference in the case of Fermi particles is that the value of z is not restricted up to 1. In the case of Bose particles, this fugacity can vary from 0 to 1. But in the case of Fermi particles, this z can take values from 0 to infinity. This z can never be negative because z is an exponential function, and exponential function will always be positive. But in the case of Bose particles, it was restricted up to a value of 1, but here it can go up to infinity. Another important aspect is, due to Pauli exclusion principle, large number of particles cannot occupy a single state. In the case of Bose particle, there is a possibility that a large number of particles occupying in a single state, and that is known as Bose-Einstein condensation. Here, there is no such phenomenon because Pauli exclusion principle doesn't allow more than one particle in a particular state. But here we will have different interesting phenomenon in the case of particles which obey Fermi Dirac statistics. Okay. Now, for large volume, the spectrum of the single particle state is almost continuous, and we can replace this summation with the integral with the density of states given by G of E dE equal to 2 pi V by h cube 2m raised to 3 by 2 epsilon or E raised to half dE. Okay. And if you substitute this in equation 1, we will get PV by KT equal to 2 pi V by h cube 2m raised to 3 by 2. These are constants. Integral 0 to infinity E raised to half log 1 plus Z E raised to minus beta E dE. Do an integration by parts here by taking log function as first function, then epsilon raised to half, integral is epsilon raised to 3 by 2 by 3 by 2 from 0 to infinity minus integral of derivative of first. Logarithm derivative is 1 by that function, 1 by 1 plus Z E raised to minus beta E, but the derivative is with respect to E. So you have to take function of a function. So derivative of this quantity Z E raised to minus beta E into minus beta. Then integral of this first function, second function, E raised to 3 by 2 by 3 by 2 dE. Okay, this first term will vanish because when E equal to infinity, this E raised to minus infinity becomes 0 and log 1 is 0. When you put the limit E equal to 0, due to this term, this boundary term will vanish. So you will get this minus and this minus becomes plus, and this 3 by 2 becomes 2 by 3. Beta will come outside. Z E raised to minus beta E, you can take the denominator, and that becomes Z raised to minus 1 E raised to beta E plus 1. This is the equation of PV by KT. Put beta E equal to x, then dE becomes dx by beta. E raised to 3 by 2 becomes x raised to 3 by 2 by beta raised to 3 by 2. Substituting that values, we will get PV by KT like this, and we can cancel from both sides. Then P by KT becomes 4 divided by 3 root pi. I multiplied with a root pi in numerator and denominator. Then the numerator, it becomes pi raised to 3 by 2. I take it that into this bracket. So 2 pi m, and this beta is nothing but 1 by KT. That makes it 2 pi m KT raised to 3 by 2 by h cube. Here is h cube. Into integral 0 to infinity x raised to 3 by 2 by z raised to minus 1 e raised to x plus 1 dx. So P by KT is, this quantity is nothing but 1 by lambda cube, where lambda is thermal de Broglie wavelength, into 4 by 3 root pi, integral 0 to infinity, x raised to 3 by 2 dx by z raised to minus 1 e raised to x plus 1. Now, we will define a set of functions which are known as Fermi Dirac functions. In the case of Bose gas, we have Bose-Einstein functions G nu of Z, but here it is represented as F nu of Z. It is defined as 1 by gamma of nu into capital F nu of Z, and it is 1 by gamma of nu integral 0 to infinity x raised to nu minus 1 divided by z raised to minus 1 e raised to x plus 1 dx. This is 1 by gamma of nu integral 0 to infinity. You take z raised to minus 1 e raised to x outside. Then in the numerator, that becomes z e raised to minus x. Already there is an x raised to nu minus 1. 1 divided by 1 plus z e raised to minus x becomes 1 plus z e raised to minus x raised to minus 1. You can apply binomial expansion here. Then this becomes 1 minus z e raised to minus x plus z square e raised to minus 2x and so on. Take this z e raised to minus x to this bracket. That becomes z e raised to minus x minus z square e raised to minus 2x plus etc. So this is 1 by gamma of nu, integral 0 to infinity, x raised to nu minus 1. This I can write it as a sum, sigma r equal to 1 to infinity, minus 1 raised to r minus 1, z raised to r, e raised to minus rx dx. I can interchange this integral and summation, then I will get it like this. Now we can convert this integral to a gamma function. So by substituting rx equal to y, x is equal to y by r, dx equal to dy by r. Substituting all those into this integral, we will get integral 0 to infinity, y by r raised to nu minus 1, e raised to minus y, dy by r. This r raised to nu minus 1 and this 1 by r becomes r raised to nu. You can take that outside. Integral 0 to infinity, e raised to minus y is here, y raised to nu minus 1 dy. This by definition, this is gamma function. So this is gamma of nu. Okay, so this gamma of nu and this gamma of nu will cancel. Remaining is integral sigma r equal to 1 to infinity, minus 1 raised to r minus 1, z raised to r by r raised to nu. When you put r equal to 1, you will get it as z. When you put r equal to 2, you will get minus z square by 2 raised to nu, r equal to 3 plus z cube by 3 raised to nu minus etc. So this is Fermi Dirac functions. In the case of Bose-Einstein functions, all the terms were positive. But for Fermi Dirac functions, the alternate terms are negative. Okay, so call this as equation number 6. Now, you can use this relation in order to find integral 0 to infinity x raised to 3 by 2 dx by z raised to minus 1 e raised to x plus 1. Okay, we have to find that value in order to get an expression for p by kt. Okay, this integral I can write it as gamma 5 by 2 f 5 by 2 of z. Okay, from this definition, when nu minus 1 is 3 by 2, this nu becomes 5 by 2. So gamma 5 by 2 will come to this side. So gamma 5 by 2 into f 5 by 2 z is nothing but integral 0 to infinity x raised to 3 by 2 dx by z raised to minus 1 e raised to x plus 1. That is this identity. Then equation 4, that is the equation for p by kt becomes 4 by 3 root pi 1 by lambda cube gamma 5 by 2 into f 5 by 2 of z. By recurrence relation of gamma function, gamma 5 by 2 I can write it as 3 by 2 gamma 3 by 2. And again gamma 3 by 2 is 1 by 2 gamma 1 by 2. So this is 3 by 4 root pi. Substituting that here, I will get p by kt is equal to 1 by lambda cube f 5 by 2 of z. But another important difference when we compared with the Bose particles is that here we have to consider a weight factor g that arises from the internal structure of the particles such as spin. Here we have particles with half integral spin and we have to multiply with a weight function and it is g. P by kt is equal to g by lambda cube f 5 by 2 of z. This is equation number 7. Similarly, equation 2. Equation 2 is this one for finding the total number of particles. Here again we have a summation. If volume is very large, we can replace this summation with an integral. So you will get this as n equal to integral 0 to infinity 2 pi v by h cube 2m raised to 3 by 2 e raised to half de by z raised to minus 1 e raised to beta e plus 1. Put beta e equal to x, then de becomes dx by beta, e raised to half becomes x raised to half by beta raised to half. Substituting that values, you will get n is equal to 2 pi v by h cube 2m kt raised to 3 by 2 and this integral. So this is n by v into multiply numerator and denominator with the root pi. Then this becomes pi raised to 3 by 2. You can take that into this 2 pi m kt raised to 3 by 2 divided by h cube and 2 by root pi. And this is nothing but gamma 3 by 2 into f 3 by 2z in terms of Fermi Dirac functions. Gamma 3 by 2 by the recurrence relation, it is half gamma half, it is half root pi. Substituting that value here, you will get n by v is equal to 1 by lambda cube f 3 by 2 of z. Again, we have to consider the weight factor g. So this becomes n by v equal to g by lambda cube f 3 by 2 of z. This is equation number 8. So we have two equations, one for P by Kt, it is equation number 7, another for N by V, it is equation number 8. In both equations, the right hand side contains a Z. By eliminating that Z between equations 7 and 8, we can find equation of state of the Fermi gas. Okay, this is the same procedure we did in the case of Bose gas also. There also we find equations for P by Kt and N by V and eliminated Z between those two equations to obtain the equation of state. Okay, so all the procedure are exactly same when we compared with the Bose gas. Okay, now we will find an expression for internal energy. By definition, it is U equal to minus dou by dou beta of log grand partition function at a constant Z and V. But dou by dou beta is nothing but dou by dou of 1 by Kt, and that is minus Kt square dou by dou t. Substituting that value here, you will get Kt square dou by dou t of log theta at a constant Z and V. But log theta is nothing but Pv by Kt. You can take this V outside, so this becomes Kt square V into dou by dou t of P by Kt. But P by Kt is G by lambda cube F phi by 2 of Z. Substitute here. Then U is equal to Kt square V G phi by 2 G into F phi by 2 Z can take outside dou by dou t of 1 by lambda cube. That is dou by dou t of 2 pi m Kt raised to 3 by 2 by h cube. And this becomes 3 by 2t into 1 by lambda cube. When you take the derivative, you will get a t raised to 3 by 2 derivative is 3 by 2 into t raised to half. Then multiply numerator and denominator with a t. Then you will get 3 by 2t into 1 by lambda cube. Substitute that value here. You will get 3 by 2 KTV G by lambda cube F phi by 2 of Z. This is the equation for internal energy. Call it as equation number 9. Okay. Now, we already know that P by Kt, the value we already know. So, if we substitute that value here, this can be written as 3 by 2 PV. Okay. For Kt, you can substitute from here. Okay. For Kt, you can substitute as P lambda cube divided by G into F phi by 2Z. So, if you substitute that value here, you will get it as 3 by 2 PV. 3 by 2 PV. So, this is a famous relation. Pressure of ideal Fermi gas is 2 by 3 of energy density. Pressure of ideal Fermi gas is 2 by 3 of energy density. Call this as equation number 10. Specific heat capacity. Once we have internal energy, specific heat capacity Cv is given by dou U by dou T at a constant N and V. This is specific heat capacity at a constant volume. We already have equation for U and an equation for N by V. So from these two equations, I can write U as 3 by 2 NKT, 3 by 2 NKT, F 5 by 2 Z by F 3 by 2 Z. Okay, so substitute for this V using this equation. Then you will get U as 3 by 2 NKT, F 5 by 2 Z by F 3 by 2 Z. Call this as equation number 11. Use this U in order to find Cv. Cv by Nk is 1 by Nk into 3 by 2 Nk. These are constants. Then dou by dou T of T into F5 by 2 divided by F3 by 2. So this is 3 by 2 into Nk and Nk will cancel. Dou by dou T of T into F5 by 2 by F3 by 2 at constant N and V. So Cv by Nk equal to 3 by 2 into, first you take the derivative of T keeping this constant, that will give you the first term. Then take T as constant and take the derivative of this term. The derivative is with respect to T, but I can apply chain rule. So I will take derivative with respect to Z, then multiply with the dou Z by dou T. Okay. And these are all at a constant V. This is small v, and small v is nothing but volume per particle, V by N. So at a constant capital N and capital V implies constant small v. So Cv by Nk is equal to 3 by 2 into F5 by 2 by F3 by 2 is here. This I can apply as 3 by 2 into T, then 1 by F3 by 2Z into derivative of this numerator dou by dou Z of F5 by 2 into this dou Z by dou T plus 3 by 2 into T f5 by 2z is constant, then 1 by f3 by 2z derivative is minus 1 by f3 by 2z whole square into dou by dou z of f3 by 2z into dou z by dou t. In order to evaluate this quantity, or in order to solve this quantity further, we want to know the values of dou by dou z of f5 by 2, dou by dou z of f3 by 2, also dou z by dou t. For finding that values, I will follow this procedure. We have n by v equal to g by lambda cube f3 by 2 of z. So f3 by 2 of z is equal to, this n by v is small n, lambda cube by g. This is n by g into lambda cube is h cube by 2 pi m kt raised to 3 by 2. That t raised to 3 by 2 will go to numerator and it becomes t raised to minus 3 by 2. Dou by dou t of this quantity is, these are all constants, then dou by dou t of t raised to minus 3 by 2 is minus 3 by 2 t raised to minus 5 by 2. Multiply numerator and denominator with a t, then this becomes minus 3 by 2 t into f3 by 2 z. Call this as equation number 12. Then take dou by dou z of f3 by 2 z. That is dou by dou z of f3 by 2 z. Fermi Dirac function is given by this equation. Taking derivative with respect to z, you will get 1 minus z square derivative is 2z. 1, 2 will cancel with the denominator 2 raised to 3 by 2 and the remaining will be 2 raised to half. Plus z cube 3z square, 1, 3 will cancel, then it becomes z square by 3 raised to half minus etc. If you multiply this with a z, you will get z dou by dou z of f3 by 2 equal to z minus z square by 2 raised to half plus z cube by 3 raised to half plus etc. And this is nothing but f half. Okay, f half of z. So this is like a recurrence relation. I can write the general recurrence relation as z dou by dou z of f nu of z equal to f nu minus 1 z. So z dou by dou z of f5 of z is f, or f5 by 2 of z equal to f3 by 2 of z. That is this one. Okay. So using this general recurrence relation, I can write this equation. Also from 12 and 13, if you divide equation 12 and 30, the left hand side becomes 1 by z into dou z by dou t. Left hand side becomes 1 by z into dou z by dou t. Right hand side becomes 12 by 13. The right hand side becomes minus 3 by 2t f3 by 2 by f half. Call this as equation number 14. Now you can go back to the equation for Cv by Nk and you can substitute for this derivative, and for dou z by dou t. So Cv by Nk equal to 3 by 2 f5 by 2 by f3 by 2 plus 3 by 2t into 3 by 2t into, this is dou by dou z of f5 by 2. From this equation, it is f3 by 2 by z. This z will go to the right hand side. f3 by 2 by z into, there is already a 1 by f3 by 2 z into dou z by dou t, plus the next term is 3 by 2t into minus 1 by f3 by 2 square is there into f5 by 2 z is there, and the next term is dou by dou z of f3 by 2. Using the recurrence relation, it becomes f half by z into, there is a dou z by dou t. This f3 by 2 and f3 by 2 will cancel, and you will get Cv by Nk equal to 3 by 2 f5 by 2 by f3 by 2 plus 3 by 2t into, what is 1 by z dou z by dou t. Here you have this relation. Substitute that, minus 3 by 2t f3 by 2 by f half, and this becomes minus 3 by 2t into f5 by 2 is here, f3 by 2 z square, and f half is here. What is 1 by z dou z by dou t? 1 by z dou z by dou t. From here it is minus 3 by 2t into f3 by 2 by f half. Now you can cancel many times. T and t will cancel. This t and this t will cancel. F half will cancel. f3 by 2 will cancel. Okay. Now if you consider the first term and last term, you have f5 by 2 by f3 by 2. In first term and last term, you have f5 by 2 by f3 by 2. In the first term, you have coefficient 3 by 2. In the last term, you have coefficient 9 by 4. 3 by 2 plus 9 by 4. It is 15 by 4. So 15 by 4 f5 by 2 by f3 by 2 What about the second term? It is minus 9 by 4 f3 by 2 by f half. Minus 9 by 4 f3 by 2 by f half. So Cv by Nk, we obtained a relation like this. Equation number 15. Now we will find Helmholtz free energy. A, it is given by mu n minus Pv, but mu is from the definition of fugacity, mu is kT log z. So substitute that. Pv, from the earlier equation you can write Pv as, we already have an equation for u, 3 by 2 nkt f5 by 2 by f3 by 2, and that is nothing but 3 by 2 Pv. From here Pv is nkt f5 by 2 by f3 by 2. This is equation number 16. Now entropy S is given by internal energy minus Helmholtz free energy by T. Internal energy U, we already have 3 by 2 nkt f5 by 2 by f3 by 2. A is minus nkt log z plus nkt f5 by 2 by f3 by 2. This is 3 by 2 plus 1, that is 5 by 2 nk f5 by 2 by f3 by 2. This temperature will cancel from numerator and denominator. Last term is minus nk log z, minus nk log z. This is the equation for entropy. So for an ideal Fermi gas, we obtained equations for internal energy, specific heat capacity at constant volume, Helmholtz free energy, entropy, etc. Okay. Now our aim is to find the properties of Fermi gas, that is all the values we obtained so far, that is internal energy, Cv, A, Helmholtz free energy, entropy, etc. in terms of particle density and temperature. Okay. So we will consider 4 different cases. The first case is known as highly non-degenerate, and the condition on N and T is N, number density is very low and temperature is very high. This is the condition for highly non-degenerate case. Number density is very low, there is very low number of particles, but temperature is very high. So the possibility of occupying a particle, more than one particle in a state is negligible. That is non-degenerate case, highly non-degenerate case. Then f3 by 2z, we already have this equation n lambda cube by g. It is nh cube by g into 2 pi m get raised to 3 by 2. For very low n and very high t, this will be very much less than 1. f3 by 2z is, by definition, it is z minus z square by 2 raised to 3 by 2 plus etc. This is very much less than 1. This is very much less than 1 happens only when z is very much less than 1. For this sum, infinite sum, to be very much less than 1, z itself should be very much less than 1. And if z is very much less than 1, I can neglect all the higher order terms, and I can write f3 by 2 of z is approximately z. And this is true for f5 by 2 z, f1 by 2 z for all new values. So in general I can say f nu of z is approximately z for highly non-degenerate case. Then what about equation 11? Equation 11 is this one. f5 by 2z and f3 by 2z, both will be z, so that will cancel and u becomes 3 by 2 nkt. U becomes 3 by 2 nkt. What about Cv? Cv, f5 by 2z and f3 by 2z are both z, and f3 by 2z and f half z both z. That will cancel. 15 by 4 minus 9 by 4. It is 6 by 4. It is 3 by 2. So Cv is 3 by 2 nk. So energy is 3 by 2 nkt. Cv is 3 by 2 nk. And Helmholtz free energy also you can find values in that special case, and that becomes A equal to nkt into log z minus 1, because here is your equation for A, nkt log z, and this will be the same. f5 by 2 and f3 by 2 will be both equal to z. That will cancel. Nkt you can take outside. So nkt log z minus 1. But f3 by 2 z, that is n lambda cube by g, that is approximately z. That is the highly non-degenerate case. So you can write instead of z the value n lambda cube by g. So it is nkt log n lambda cube by g minus 1. S is entropy. S is nk into 5 by 2 minus log z, and z becomes n lambda cube by g. So this was our aim. obtain the quantities, properties of Fermi gas in terms of temperature and number density. Now all the equations contains only temperature or number of particles. Okay, but in these equations Cv by Nk, A, S and U, this contains Z. Okay, now in this particular special case we obtained these values in terms of the variables temperature and number density. But this is a special case and it is known as highly non-degenerate case, and this happens when T tends to infinity, temperature tends to infinity. Now case 2. Here Z is less than 1 but not very small. In the first case you have Z very much less than 1, but here the case is Z is less than 1 but not very small. That is, temperature is not tending to infinity. It is a finite temperature but very high temperature. Okay, in terms of temperature we can say that for case 2 temperature is high but not infinitely high. Then we can make use of the definition f nu of Z equal to Z minus Z square by 2 raised to nu plus Z cube by 3 raised to nu, etc. to eliminate Z between equation 7 and 8. From 8 we have n by v equal to g by lambda cube f3 by 2z. You can write it as n lambda cube by g equal to f3 by 2 of z. You can substitute here. So that becomes Z minus Z square by 2 raised to 3 by 2 plus Z cube by 3 raised to 3 by 2 minus etc. Now we are going to invert this series in order to obtain Z as a function of n lambda cube by g. Exactly same procedure we did in the case of Bose gas also. So I will explain once more. Inversion of a series. Suppose you have a series like y equal to a1x plus a2x square plus a3x cube plus etc. You want to invert this in order to get x as a power series in y. That is x equal to capital A1y plus a2y square plus etc. For finding capital A1, A2 etc. we can do the following procedure. Substitute this x here. Then you will get y equal to a1 into, instead of x you substitute this series, instead of x square you substitute that series plus etc. Now equate the coefficient of y on both sides. On the left hand side you have 1, on the right hand side you have small a1 into capital A1. So capital A1 is 1 by A1. Equate coefficient of y square on both sides. Left hand side it is 0, right hand side you will get some coefficient, write those. Then a2 will be minus a2 by a1 cube. Similarly, equate coefficient of y cube on both sides, you will get a3. Equating coefficient of y4 on both sides, you will get a4 and so on. Now, here we have n lambda cube by g equal to, this is the series. So instead of x here you have z. Instead of y you have n lambda cube by g. Instead of a1 we have 1. Instead of a2 we have minus 1 by 2 root 2. 2 raised to 3 by 2 is nothing but 2 root 2. Okay. So substituting in these equations you can find capital A1, capital A2, capital A3 etc. And thus that values will be a1 equal to 1, capital A2 equal to plus 1 by 2 root 2, capital A3 equal to 1 by 4 minus 1 by 3 root 3 and so on. So this inverted series x equal to a1y plus a2y square becomes z equal to n lambda cube by g plus 1 by 2 root 2 n lambda cube by g whole square plus etc. So we inverted the series in order to get z as a power series in n lambda cube by g. Now you can use that here in the equation for p by kt. So substitute for this set the series in n lambda cube by g. For z square also you substitute that series. For z cube you substitute that series and so on. Now group the coefficients of various powers of n lambda cube by g. N lambda cube by g square you have 2 times. N lambda cube by g whole cube you will have 4 times and so on. Group those terms. Then this is p by kt. If you multiply with a v and divide with an n, this becomes pv by nkt. Then the right hand side becomes g by, this n is actually capital N by v. So g by n lambda cube into this n lambda cube by g plus higher order terms. Now you can take this term into the bracket. Then first term becomes 1, Second term becomes n lambda cube by g into 1 by 4 root 2 plus higher order terms. So this is PV by NKT. PV by NKT equal to, you can write this as a sum sigma L equal to 1 to infinity minus 1 raised to L minus 1 AL n lambda cube by g raised to L minus 1. Okay, but this small n I can write it as 1 by small v, and small v is volume per particle. So PV by NKT equal to sigma L equal to 1 to infinity minus 1 raised to L minus 1 AL lambda cube by GV raised to L minus 1. Equation number 80. Similar expression we obtained in the case of Bose gas also, but the difference was this term is not there. Minus 1 raised to L minus 1 is not there. Okay, so here you have alternate negative signs, but in the case of Bose gas, the terms are positive, and AL are known as virial coefficients. Okay, so this is the equation of state for ideal Fermi gas. Now you can calculate a specific heat for the case 2. Okay, so CV by Nk equal to 1 by Nk into dou U by dou T at a constant N and V. This is 1 by Nk into dou by dou T of U is 3 by 2 PV. You can take this Nk into the bracket, so that becomes 3 by 2 dou by dou T of PV by Nk. So from here PV by Nk is T into this summation, T into that summation. So you apply product rule, 3 by 2 into, first you take the derivative of T, that will be 1 into this quantity. Then you keep T as constant, 3 by 2 T, take the derivative of this quantity. And in this quantity, the only temperature dependent term is lambda cube. So you take the derivative of lambda cube raised to L minus 1. That is dou by dou T of lambda raised to 3L minus 3. Dou by dou T of lambda raised to 3L minus 3 is nothing but minus 3 by 2T into L minus 1 lambda raised to 3L minus 3. Now I will explain how we obtained this equation. So dou by dou T of h cube by 2 pi mkt raised to 3 by 2 raised to L minus 1. The only temperature dependent term is this one. So I can take all other terms outside. H raised to 3L minus 3 by 2 pi mk raised to 3L minus 3 by 2 into dou by dou T of 1 by T raised to 3L minus 3 by 2. The derivative is minus of 3L minus 3 by 2 into T raised to minus of 3L minus 3, that becomes minus 3L plus 3 by 2 minus 1. Because derivative of x raised to n is nx raised to n minus 1. Multiply with a t and divide with a t. So this t raised to minus 1 will go, and denominator will have a t. So this is minus 3L minus 3 by 2t, h by root 2 pi mk raised to 3L minus 3, and this becomes t raised to minus 3L plus 3 by 2. Okay, so you can take this quantity into this bracket, that will give you minus of 3L minus 3 by 2t h by root 2 pi mkt raised to 3L minus 3. So that is nothing but minus 3 by 2t into L minus 1 to lambda raised to 3L minus 3. Okay, so substitute this value here. So you will get CV by Nk equal to 3 by 2 into sigma minus 1 raised to L minus 1 AL lambda cube by GV raised to L minus 1 minus 9 by 4 sigma minus 1 raised to L minus 1 AL into L minus 1 by GV raised to L minus 1 into lambda raised to 3 into L minus 1. Here you have two terms, minus 9 by 4 into minus 1, that becomes plus 9 by 4 into sigma minus 1 raised to L minus 1 AL lambda cube by GV raised to L minus 1, and the second term is minus 9 by 4 into this L. So minus 9 by 4 sigma minus 1 raised to L AL into L lambda cube by GV raised to L minus 1. The first two terms, adding the first two terms, you will get 15 by 4. 15 by 4 into this quantity, and that is written here 3 into 5, 15 by 4. That is the first quantity, and the last quantity is minus 9 by 4 into this quantity. So 3 by 2 into minus 3 by 2, that becomes minus 9 by 4 L into this quantity. So this expression can be simplified like this. So you can take this Nk to the right hand side. Cv equal to 3 by 2 Nk. When you put L equal to 1, this becomes minus 1 raised to 0, that is 1. this L is 1. So 5 minus 3, 2 by 2 becomes 1. A1, virial coefficient A1 is 1. And this L is 1. So 1 minus 1, 0. Any quantity raised to 0 is 1. So the first term will be 1. And the second term will be a negative term. And the third term will be a positive term, and so on. So this is the expression for CV. And this is a series in lambda cube by GV or n lambda cube by G. For t tends to infinity, that is the case 1. For t tends to infinity, lambda tends to 0, and you can neglect all these terms. So we will reduce to the first case, CV equal to 3 by 2 nk. Okay, the result we obtained in case 1. But for finite temperatures, that is temperatures not infinitely high, for finite temperatures, CV will be less than 3 by 2 nk, because you can see that 1 minus a quantity. Okay, so 1 minus a quantity means for finite temperatures this will have value and CV will be less than the 3 by 2 nk value. Okay, so CV will be less than the limiting value. So we can say that CV of ideal Fermi gas decreases with the temperature. For infinitely high temperature it is 3 by 2 nk, and for finite temperatures it is less than 3 by 2 nk. That is, we can say that CV of ideal Fermi gas decreases monotonically with the temperature. I will compare this result with the result for Bose gas. This is the graph of CV of Bose gas. You can see that for infinitely high temperatures, CV is 3 by 2, that is 1.5 nk. But it is not a monotonically decreasing function. It increases first and reaches a maximum and then decreases to 0. That is the behavior for Bose gas. The CV, specific heat capacity of Bose gas, behaves like this. At infinite temperatures, it is 3 by 2 nk. When temperature decreases, it increases first and then reaches a maximum and then decreases. But for Fermi gas, the behavior is like this. It is a monotonically decreasing function with the temperature. The high temperature limiting value is 3 by 2 nk, but as temperature decreases, it monotonically decreases to 0. That is the difference between Bose gas and Fermi gas in the case of specific heat capacity. Now, suppose n and t are such that n lambda cube by g is of the order of unity. Okay, n lambda cube by g is of the order of unity. Then this expansion will not be useful. N lambda cube by g, if it is of the order of unity, this cannot be of very much use. If this quantity is very small, we can use this expansion and we can neglect higher order terms. But if this quantity is of the order of unity, we cannot make use of that expansion. Then we have to recourse to numerical calculations. But if n lambda cube by g is very much greater than 1, okay, is very much greater than 1, then the functions can be expressed as asymptotic expansions in powers of 1 by log z. That we will discuss later, and that condition is known as a degenerate case. Now we are going to discuss the extreme case, that is n lambda cube by g tends to infinity. Its value tends to infinity, and that corresponds to the case when n is very large, number density is very large, and temperature tends to 0. Temperature is very low. Okay, this is the extreme case. Temperature tends to 0. Then these functions u, cv, Helmholtz free energy, entropy, etc. will assume a closed form, and the thermodynamic quantities becomes highly simplified. Okay, and the gas is known as completely degenerate. N lambda cube by g greater than 1 condition is known as degenerate. N lambda cube by g tends to infinity is known as completely degenerate. N lambda cube by g tends to 0 is known as highly non-degenerate. Okay, that are the different cases. So n lambda cube by g tends to 0 we already discussed. N lambda cube by g less than 1 or very much less than 1 also we discussed. N lambda cube by g is of the order of unity. It is not possible to explain using these expansions. N lambda cube by g very much greater than 1 we will explain later. Now we will explain the case n lambda cube by g tends to infinity, and that is known as completely degenerate case. Call this as case 3. and this happens when t tends to 0, that is n lambda cube by g tends to infinity. The mean occupation number is given by 1 divided by e raised to e minus mu by kt plus 1. When t tends to 0, depending on whether e greater than mu or less than mu, this occupation number can take value 1 or 0. If e is less than mu, then this quantity will be, numerator will be negative, and when t equal to 0, this becomes e raised to minus infinity. E raised to minus infinity is 0, so this becomes 1. If e is greater than mu, this numerator is a positive value. When t equal to 0, this becomes e raised to plus infinity. E raised to plus infinity is infinity, so 1 by infinity is 0. That is, the occupation number will be a step function, this red curve. For t equal to 0, okay, for t equal to 0, absolute 0 temperature, for energy less than mu, this mu 0 is nothing but the value of chemical potential at absolute 0. Okay, so for energy less than this chemical potential, occupation number is 1. For energy greater than this chemical potential, occupation number is 0. That is this graph, this red one. Okay, so what is the meaning? At t equal to 0, at absolute 0 temperature, all single particle states up to the energy E equal to mu naught are completely filled with one particle per state, while all other single particle states with energy greater than mu 0 are empty. Occupation number is 0 means all other states are empty. So the limiting value mu 0 of single particle energy is called Fermi energy, and I will denote it as EF. And the corresponding momentum is known as Fermi momentum PF. Corresponding temperature we can call it as Fermi temperature TF. Now we will calculate these quantities: Fermi energy, Fermi momentum, and Fermi temperature. Suppose there are n particles in the system. Then these particles are filled up to the Fermi energy at absolute 0 temperature. So these particles are filled up to Fermi energy. So integral 0 to EF g of E dE, this is density of states. If you integrate this quantity, you should get total number of particles, because all these particles are distributed up to Fermi energy. Beyond Fermi energy, there is no particle. So integral 0 to EF g of E dE equal to n. G of E, we already have the expression, and you have to add this weight function. So g into 2 pi v by h cube 2m raised to 3 by 2 e raised to half dE. Substituting that values here, this integral of e raised to half is e raised to 3 by 2 by 3 by 2, and simplifying that you will get 2m EF raised to 3 by 2 equal to 3 by 4 nh cube by pi GV, and EF Fermi energy is equal to 3n h cube by 4 pi GV raised to 2 by 3 into 1 by 2m. This is the equation for Fermi energy. This n, capital N by V, you can write it as number density. So 3n by 4 pi g raised to 2 by 3. H cube raised to 2 by 3 is h square. So h square by 2. That means Fermi energy is proportional to number density raised to 2 by 3. As number density increases, Fermi energy also increases. Not linearly, but less than that. Okay, it is around 0.67. So EF increases with the n. Now, h cut is h by 2 pi. So you can write h square as h cut square into 4 pi square. So this becomes h cut square by 2m into 6 pi square n by g raised to 2 by 3. But energy is p square by 2m. P is h cut k. So that is h cut square k square by 2m. Comparing these two equations, I can say that k is 6 pi square n by g raised to 1 by 3. This is known as Fermi wave vector kf, 6 pi square n by g raised to 1 by 3. Fermi momentum Pf is h cut kf. It is h cut into this value, 6 pi square n by g raised to 1 by 3. So Fermi momentum is proportional to n raised to 1 by 3. So as n increases, Fermi momentum will also increase. Fermi temperature Tf is Ef by k. It is h cut square by 2 mk into 6 pi square n by g raised to 2 by 3. Now we will consider another important aspect of Fermi system, 0 point energy. This is nothing but the energy of the system at absolute 0, that is at t equal to 0 Kelvin. I will define that energy as E0, and that is the total energy of particles up to Fermi energy. So integral 0 to EF G of E into dE. Okay. So E0 equal to, substitute for this density of states, you will get 2 pi GV by h cube 2m raised to 3 by 2 integral 0 to EF E raised to 3 by 2 dE. If you integrate that, you will get it as E0 equal to 4 pi GV by 5 h cube 2m EF raised to 3 by 2 into EF. But 2m EF raised to 3 by 2, we already have an expression from here. So substitute this value. Then you will get it as E0 equal to 4 pi GV by 5 h cube into 3n h cube by 4 pi GV into EF. Cancelling the terms, you will get E0 by n, that is 0 point energy per particle, is 3 by 5 Fermi energy. 3 by 5 of Fermi energy, or 3 by 10 of Fermi momentum square divided by m. This is 0 point energy per particle. Now you can calculate the ground state pressure P0. By definition, it is 2 by 3 into 0 point energy by V, because P is 2 by 3 U by V. Here it is ground state pressure, that is energy of ground state or energy at T equal to 0. Substitute for U E0. Then P0 is 2 by 3 E0 by V. So P0 equal to 2 by 3 into, what is E0? It is 3 by 5 NEF into 1 by V. So P0 is, ground state pressure is 2 by 5 NEF. But EF is this one. This equation we already derived. Substitute for this EF. You will get ground state pressure is proportional to n raised to 5 by 3. So at T equal to 0, there is a positive energy and there is a pressure. That is, the molecules are still moving. There is a ground state pressure means the molecules are still moving. Even at 0 Kelvin, the molecules are moving. So there is 0 point motion, and it is a purely quantum effect. And this arises due to Pauli principle. Because at T equal to 0, all the particles cannot sit in the ground state. Okay, it is not allowed by Pauli exclusion principle. According to Pauli principle, each state can occupy maximum of one particle. So if there are n particles, that should be spread over a requisite number of energy levels. That is, at T equal to 0 itself, Fermi gas or Fermi system is quite live. Okay, it will exert a pressure, it will have a 0 point energy and all. Okay, so this is the characteristic of a system consisting of Fermi particles. So I am going to stop at this point. Case 4 we will consider in the next lecture. Thank you.